The second type of distribution we want to review is a discrete distribution. A discrete distribution is a distribution where the potential results are finite, or a countably infinite number of possible results based off of a set of discrete variables. A countably infinite number of results means that a person can count all the data points, such as real numbers, even though it will take a long time. You can count it in a finite amount of time. A good example of a discrete distribution would be a distribution of home runs by each Major League Baseball player. There will be a discrete set of home runs, maybe 0 to 100. Each player will hit a certain number of home runs, and the home runs will fall into the discrete classes or ranges of home runs. A player will not hit 1.2 or 30.7 home runs, but will hit 1 or 30 or 40 or 22. These are discrete numbers. As we see, each bin has a range of discrete home run totals that each player could hit. This is a discrete distribution. Now that we have gone through an example of what makes a distribution and looked at two different characteristics of distributions, continuous and discrete, we will explore what is probably the most famous distribution, the normal distribution, aka the bell curve. The normal distribution, also known as the Gaussian distribution, resembles a bell curve and is one of the most famous distributions in analytics. Here we have an illustration of a normal distribution. Let's examine what we have in front of us. A normal distribution is distinguished by the bell-shaped curve that the data present when visualized. When looking at a normal distribution, half of the results fall above the mean and half the results fall below the mean. One other fun anecdote about the normal distribution is this: the mean equals the median, which equals the mode. So what does the normal distribution show us? The normal distribution plays part in one of the most common and famous parts of statistical analysis, standard deviation. The standard deviation is a common tool used in analytics that measures the dispersion of a data population. When looking at the actual number that represents the standard deviation, a low standard deviation can show us the numbers are not very dispersed and will hover closer to the mean. A high standard deviation can show that our data is very dispersed and will be more spread out away from the mean. In essence, the standard deviation is a measurement of how spread out the data is. The standard deviation is usually designated by the Greek letter sigma, and the mean is usually represented by the Greek letter mu. So what does dispersion mean? What is the standard deviation showing us? This is the magic of the standard deviation. If we look back at our example normal distribution, the standard deviation will show us how dispersed the data are. Let's assume the data we are looking at is the average weight of men in a given population. Granted, this isn't necessarily normally distributed, but in our case, we will say it is for example purposes. In our case, the mean is 185 pounds, and the standard deviation is 12 pounds. That means one standard deviation away from the mean is 173 pounds and 197 pounds. Two standard deviations away from the mean would be 161 and 209 pounds, and so forth. The best part of this is what the standard deviation shows. The standard deviation shows us that within plus minus one standard deviation away from the mean will fall 68.27% of all the data values within the population. Within plus minus 2 standard deviations will be 95.45% of all the data values within the population. And within plus minus 3 standard deviations will fall 99.7% of all data values in the population. Let's visualize this using our chart. Remember, in our example, we know the mean weight is 185 pounds and the standard deviation is 12 pounds. To plot that on our chart, we will see the mean weight of 185 pounds in the middle. Then we will plot plus 1 standard deviation and minus 1 standard deviation. With those standard deviation lines, the area represented between those two lines will contain 68% of all the weights in the population. If we then plot plus 2 and minus 2 standard deviations, we are now capturing just over 95% of all weights in the population. This is the power of the standard deviation. Within just 2 standard deviations, we are capturing 95% of all of the data points within the population. One note, this works on samples or entire populations. And if the sample is done properly from the overall population, we can then infer things from the sample that would translate to the larger overall population. This is a powerful analytical tool from distribution analysis. One question that should be very easy for us to answer is, are all distributions shaped like the normal distribution? Of course, the answer is no. Another characteristic of distributions is skewness. Skewness is a measure of lack of symmetry in the distribution. Essentially, this means it is not uniform around the mean. If it is skewed to the right, it is positively skewed, and the distribution looks like the following. Positively skewed means that the tail drags to the right of the chart. If it is skewed to the left, it is said to be a negative skew, and the longer tail will drag out to the left. Some notes on skewness. If the distribution is skewed negatively with the tail dragging left, then the mean will be less than the mode, and vice versa. If the skewness is positive and to the right, then the mean is greater than the mode. We now want to cover a couple more potential characteristics you might see with distributions. Please note, the characteristics and details we have covered in this module do not represent all the different characteristics of distributions that exist, but will give you a background and foundation for this part of analytics. Our next type of distribution and characteristic is a bimodal distribution. What do we think bimodal means? Well, the prefix of bi means two, and modal has to deal with mode. So we have two modes or two different peaks in a chart. That is pretty straightforward. So let's look at a chart that would show this. Here we can see two peaks that exist within our distribution. There is an actual mode to our data, 55. But because of the way the data are dispersed, we can see a bimodal set of peaks within our distribution. The highest peak in the distribution is called the major mode. The second peak is called the minor peak. So if bimodal means two peaks, what do we think multimodal would mean? Multimodal means multiple peaks. Here is a chart showing a multimodal distribution. A multimodal distribution has two or more peaks. One key takeaway from a multimodal distribution is it is a strong indication our data or distribution is not a normal distribution. This would make sense if we think back to our normal distribution we reviewed earlier in the module. In this module, we have covered a few different items regarding distributions. Let's ask you a few questions to see if this information has stuck. Question 1. What is one common way a distribution is visualized? The answer is either a histogram or box plot. Remember, a histogram looks like a bar chart and is designed to show the frequency of occurrences of actual or predicted results, measured against bins or ranges of data. A box plot shows 5 descriptive statistics numbers: minimum, maximum, first quartile, third quartile, and median. Question 2. How many standard deviations will encompass 95% of the data? The answer is 2. Remember, one standard deviation will encompass 68% of data points. 2 standard deviations will encompass 95%. And 3 standard deviations will encompass 99.7%. Question 3. A normal distribution looks like what shape? The answer is a bell curve. In a normal distribution, the mean equals the median, which will equal the mode. Question 4 and final question. A distribution with 2 peaks is called what? The answer is a bimodal distribution. A distribution with 2 or more peaks is a multimodal distribution. We have covered a lot in this module on distributions. Let's review what we have covered. We walked through an example to help us understand what a distribution can show us. As you may remember, a distribution is an orientation of data points, broken down by their observed or predicted frequency of occurrence. Our example distribution showed different bars that represented the number of students scoring a certain result on the test. We looked at 2 different types of characteristics of distributions: continuous and discrete. A continuous distribution is one that has an infinite amount of possibilities in the range of values, whereas a discrete distribution only has distinct values that can be measured in the distribution. Think of possible percentages on a test score versus number of home runs hit. We looked at the normal distribution, also known as the Gaussian distribution, which can take on the shape of a bell curve. The normal distribution can help us to utilize the analytical tool of standard deviation. Finally, we looked at skewness as a part of distributions, and also looked at bimodal and multimodal distributions. This module represented the last module in a series of 3 modules regarding data: understanding data, understanding aggregations, and finally, understanding distributions. We hope you utilize these modules to enhance your data and analytical literacy. We also hope you will utilize the other courses within the Click Continuous Classroom to enhance your technical and analytical skills. This represents the end of the video experience associated with this learning module. Please close this browser window, return to the course, and complete the remaining elements.